have, or say how many buckets, as a parameter, we specify how many buckets we want, then we can run that. Now this is a pure C implementation now. Of course, if you use the OpenCV function, then it will be significantly faster because it's a C++ code, vectorized C++ code that runs a lot faster. And then I can draw that space. Now, in our original representation, a single pixel, edge pixel, would correspond to a line in the Huff space, which would be all the possible lines going through that pixel. In the sine-cosine format, we don't get lines, but we get sine curves. So if I then take the Huff space, convert it to an image, and false color code it, print it out, then we can see what the accumulated space, what the result of the votes is. Now I think I used up too much memory. So then it says it found the maximum line, which I think has parameters 193 and 4 row, and about 90 degrees for A, or theta. And then I can draw it into the image. Yes, the visualization. So this would be the Huff space using the sine cosine representation. The red point is where the maximum exists. So lots of sine cosine curves overlay there. So this is the line that is supported by the most number of edge pixels. And then here I have a small output, sample output, with some random pixels that I generated. For this particular shape, this would be the line that was found. Now, because of the discretization, it is reasonably robust with respect to noise, because if a pixel shifts by a little bit, most likely it's going to stay in the same bucket. So that's a nice feature of the algorithm. So this is a very nice, very powerful algorithm. Now, there's a couple of caveats, a couple of things that you need to be aware of that are important to realize. The first thing to realize is this is a voting scheme. So the Huff algorithm is going to return the line with the most number of votes, which corresponds to the, since each pixel can vote for lines, that means it's the line with the most number of pixels in it. So that means it's the longest line in the image that could possibly exist, which is not the same as the longest line in the image that you will actually see. So here we have an example of a picture, and if I run the Huff transform, the Huff algorithm on this particular line, this particular image, then what will be the line that it detects? So maybe I should have drawn them different directions. This one is a little bit boring, but which one would be the longest line? This is not an optical illusion or anything like that. Most people will say that the longest line in this particular image is this line here at 150. Right? Clearly it's longer than the other ones. That's not the line that your Huff algorithm finds. The Huff transform will find, any ideas what the longest line in that image actually is? If you run the Huff algorithm on this image and show the output, then surprisingly, here's your Huff space. So we find a maximum. Where's the line? Here. The longest line that your Huff algorithm actually finds would be this vertical line. This horizontal line. Why? Because there's one pixel here, one there, one there, one there, one there, one there. If you add them all up, you end up with more pixels than what we had at 150. Right? So again, the Huff space and similar algorithms will return the longest possible line in the image. Now, you wouldn't consider this to be the line because the gradient information here is wrong, right? It should be vertical lines. They should not be able to vote for horizontal lines, basically. And that's the extension to actually the Huff algorithm that is usually implemented. Instead of voting, so the problem with the Huff algorithm is that it finds the line that is supported by the maximum number of pixels, but that may not correspond to what you consider to be the longest possible line in the image. So in the example above, it gives us an incorrect line because none of those, most people wouldn't detect any horizontal line in that image, never mind the strongest or most prominent line being the horizontal line. The problem is that the Huff algorithm does not consider the gradient of the edge pixels, and so that means that edge pixels that are on vertical edges can vote for horizontal lines. which shouldn't really be possible, right? If you have an edge like this, some shape here, and you have a vertical edge, you don't want the algorithm to say, oh yeah, some horizontal line going through here. So we can fix that by changing our voting procedure. Instead of having it democratically, each pixel gets one vote. Now it's more the Chinese version, so now some pixels get more votes. The voting is limited by the local gradient, which we can calculate and detect using Sobel X and Sobel Y. And then we provide, instead of giving one vote, we allow it to vote with 1 minus the difference between the local gradient and the gradient of the line that you actually would be voting for. So if there's a vertical edge and your local gradient is vertical and you're voting for a of 0 degrees, then you get to go cast a full 1 vote. If it's off by 10 degrees, your vote is slightly less. If it's off by 90 degrees, you probably want to restrict it and say that the weight is very small, in this case, so almost 0. Which means you don't get to vote for lines that don't match your local gradient. And then lastly, detecting multiple lines. If you have a look at the output of our half space, on the actual full-size image, here, then you can see, okay, this is the maximum, but there's clearly also some line artifact here, right? And some line artifact there, and some line artifact there, where multiple pixels overlap. And you would think that, okay, then I just extract multiple lines out of the Huff space. Now, in practice, that can work, but it can also fail because some of these volts were generated by this line here. So now if you detect this line and then you say the next strongest one is that one, that may actually be, you may be counting the same pixel twice. So to do it properly, you need to make sure that the maximum, if you go to the next line, you want to pick a line that is not too close in the image, because otherwise it's probably the same line that just got split over multiple buckets in your discretization. If they are far enough apart, then it usually works quite well by just looking at the next maximum. But if you need the correct solution, what you actually have to do is go through the image, pick the edge pixels that match the first line that you found, remove all of these edge pixels, and then run the entire Huff algorithm again. Computationally, that would be too expensive. That's usually not done, certainly not in real-time applications. You may do it for certain other applications. For example, this one was kind of interesting. decades ago. So declassified images from the Middle East, from spy satellites. The US released them, and using those images, they found 400 forts, military barracks of the Romans in that area that they didn't know existed before. So this now means that historians know that there were a lot more Roman forts than they thought they were there. And if you have this kind of application, then of course real time is not really a concern, right? So you could then try and extract the exact shape of the fort so that when you start digging, you actually hit the thing, right? The treasure chamber or something. But a very nice application of computer vision. You can see detecting these kind of shapes would be difficult using any other kind of algorithm. So, I like that application. So in that case, you would erase the pixels for the wall that you found and then rerun the entire Hough transform. Another problem is that when you look at the Roman fort problem, the Hough transform will return the equation of a line, but it's a mathematical line, which means that it's a line that runs from minus infinity to plus infinity. In our image, we usually care about the line segments, right? We need to know the start and the stop of the line. We're not interested in infinite length lines usually. So to find the line segment, that one is not too difficult. You start at one edge of the image and keep going until you find an edge pixel. The first edge pixel that you find is usually considered the start of the line segment. Then you keep going along the line. If it breaks, so there's several pixels, usually not just a single one, but multiple pixels that are not there, then you would say this is the end of the line segment. Then you keep iterating doing that. So you follow the equation of the infinite line, looking for start and stop ends of segments in order to generate your line segments. And then there's different parameters, implementations that you need to consider. For example, if it's an artificial image, then you may be able to, then you could maybe be sure that there's no holes in the outline, in which case, as soon as a single pixel misses, you would say this is the end of the line segment. In realistic images, there's quite a high chance that some of the edge pixels are below the threshold. And then you can say, okay, well, maybe I allow a hole of a maximum size of 1 pixel or 2 pixel or 5 pixel, or a certain density of pixels around that area, in which case you continue the line segment, otherwise you cut it and stop it. And that's the Hough line algorithm, Hough transform algorithm for detecting lines. Now, the interesting thing about the Hough transform is that we can actually use it not just to detect lines, but any other kind of shape that we can parameterize. So the Hough transform can also be used in order to detect circles. So how would it look? How would it work for circles? What would be the parameters of a circle? in order to draw a circle, what information do you need? The radius, right? What you indicated, and the center, right? Which means we need to know the x and y coordinates of the center as well as the radius. So that means we have 3 parameters. For a line, we only have 2 parameters, right? A and B, or theta and rho, 2 parameters. So that means that our half space for circle detection would be 3-dimensional. Here we would have R, and here we have Cx and Cy. But then we continue the same processing. We now iterate through, I guess we would iterate through Cx and Cy. Right? So if I have an edge pixel in my image, some edge pixel here, then I can say, oh, here's my pixel P1. If the center is here, right, then I can calculate what the radius of this would be. So now, let's say the radius is 0.5, and for this particular pixel here, I then have a little box, right, and I add 1 to it. Now, the way that this space then looks like means that for this pixel P1 here, at this radius 0.5, that's going to look like a circle around, right? Because if the center is here, and this is R, and this is R, and this is R, for different possible centers of the circle would go through pixel P1. So for constant R, the possible centers would be located around the pixel P1 in a circle. But then you can also say, oh, if the center is here, right, then you will get a different R. So if R is greater, so 1 meter, then you would have another circle here that corresponds to a larger circle around position P1. But so instead of running an accumulator in 2 dimensions, we now run it in 3 dimensions. And that's how we can detect circles in a half space as well, by looking for the maximum. So this is also a very common algorithm that you can use, but you can do it even more varied. In fact, that's usually called the generalized Huff transform. Which corresponds to any shape that you can describe using a fixed number of parameters. So if you want to detect I don't know, some logo of your sports team, and it looks like this, then you can also parameterize that, because you may have, for this particular shape, right, you would have a position, so pick one pixel that you use in order to define the position of this. Then you can go through and say, oh, if you have an edge pixel, then you would need to iterate through saying, oh, if that edge pixel matches here, then the position of that shape would be Cx, Cy. Right? If I now assume that that edge pixel matches somewhere else, let's say it matches this pixel here, this one here, then the position of that shape would be down here. Right? Be shifted down a little bit. If I find a pixel, this pixel here is an edge pixel, and now I say, oh, if this pixel matches the shape exactly at this position, that would be the position. But if that edge pixel is actually this part, then the center of it would be down here somewhere. Because then the shape would look like this. Right? And if it matches the other one, then it would be shifted over to the right. Right? So doing this, I can calculate the maximum likelihood or the maximum voted for position of the shape in the image. Then I can detect those. Of course, that would be too simple application usually of the generalized Hopf transform, because we can just run cross correlation or template matching in order to find that exact shape with the maximum. I wouldn't need to run the Hopf transform. However, now let's say that this shape, the camera can move, so I need to know the scale of this thing. I can zoom in, zoom out. Right? In that case, I now have three parameters, Cx, Cy, and now the scale of it. Right? So then you say, oh, if the scale is 1, then this would be the center position. If the scale is 2, then this would still be the center, but if the scale is 2, then for the orange one, it would be further down here somewhere. Right? Because now it would be the doubly sized shape. If I zoom in for scale of 2. So then I would have a three-dimensional accumulator space. And lastly, if the shape can rotate, then I need to have a four-dimensional accumulator space, because now I have scale and also some rotation angle theta that shape may have. And all of that. Now this is a very flexible thing, right? We can use that in order to detect the Roman fourth, for example. Because they would have different orientation in the image, they would have different scales, but the Hopf transform is going to pick that out basically as reasonably slanted or reasonable sized rectangle. And so of course you can also detect rectangles between them. So it's a very powerful general purpose algorithm. One issue is that the size of your accumulator space grows with the number of dimensions that you have. It doesn't grow exponentially, but it's still, if you have two parameters, then it's sort of n squared, right? If you have 3, then it's n cubed. Even for small n that starts growing very quickly, especially because you need to have it in memory, so you can add like +1 to it. Right? Then if it has 4 n to the power 4, that's sort of the limit. If you have more than 4 parameters, you need to, then just running a general Huff transform will mean that you get, it's not just a problem with the memory space in the runtime, also since you're splitting it up into multiple possibilities, there's also the chance that you have some spurious correlation which allows you to see shapes that are not really there. So in that case, if you have more than 4 parameters for a shape, you can still do things like, look at the neighborhood. If you're trying to detect this shape, then what you would want to do would be to just look for the baseline and the height here, and then calculate what the scale would be. Right? The scale you should be able to get, if you have a couple of pixels here in this neighborhood, you'll probably be able to figure out what the scale is, rather than simply guessing and saying, oh, this could be anything from like 1 pixel to 1,000 pixels. Right? That's not going to be very successful approach, most likely. So the more you can restrict your choices, the more likely you are to actually extract the correct shape. But this generalized Huff transform with the idea of voting for the most likely candidate is a very nice way of reformulating a computer vision problem. Right? Because now it is, instead of a detection problem, it's now basically a parameter estimation problem. Okay, good. Then we have another set of slides you can just run through. So here's an implementation of the Huff-Line algorithm using OpenCV implementation. So this is just calling the OpenCV Huff-Line and randomized probabilistic Huff-Line algorithm, which runs slightly faster by making some more decisions about the gradients and the direction of the edges. And here's our input image. And you can play around with the parameters to get different outputs of your Huff-Line algorithm. So here's the output of the Huff-Lines. OpenCV implementation, you can see those are infinite lines, so they stretch across the entire image. And then here's the Huff-Lines P algorithm for the probabilistic Huff-Lines algorithm, which returns line segments. So then we can detect line segments that were found using the probabilistic Huff-Line algorithm. Now the parameters of these algorithms are sort of what you would expect from the description of it. You need to determine the size of your buckets for rho and for theta, right? Because that will make a difference in your algorithm. And then the minimum number of volts and the minimum line length are extra parameters that you can set in order to ignore tiny lines or lines that are not long enough to meet your particular requirements. And there's also implementation of the circle detection algorithm in OpenCV. So you can use OpenCV in order to detect circles using the Alpha library. Also very easy. Okay, good. So that's it for today. On Monday, you will have the demonstration for the assignment. So make sure that you contact Ilham or Rifki in order to set up an appointment with them Monday afternoon in order to demonstrate your assignment number 1. And then I'll post assignment number 2 sometime next week.